All right, hi there. This is Dr. Matthew J. Traum. I am your instructor for EML 4501 Mechanical Engineering Design 2 at the University of Florida. This is the first online lecture of the course. I'm going to share with you a little bit about myself as a way of introduction and share some course goals. We are going to talk a little bit more about me, where I came from, how I got here in the face-to-face lecture in the first week of class, but there are more details in this online presentation than I'll have time to talk about with you guys face-to-face. So I think the best way to explain how I got here is to share with you where I've been. So here's a map of the US, and my story really starts at the University of California at Irvine, which is in Orange County in Southern California, where I was a mechanical engineer and aerospace engineer double major at UCI. Now, at UCI, I got to work on a number of really cool undergraduate research projects. At the time, renewable and alternative energy was a really big deal, and so I worked at APEP, which was the Advanced Power and Energy Program, and I got to work on projects that included molten-carbonate fuel cells, photovoltaic cells, aero-derived microturbines, and ambient air quality monitoring. And this worked out pretty well, because when it came time to graduate, I was not required to do a capstone project, but I decided to go ahead and do one anyway. And I ended up having my project sponsored by a company called Nextek Power Systems. And the Nextek project was to connect the photovoltaic array in the APEP building to the lights in the visitor gallery at the National Fuel Cell Research Center, using some of the energy monitoring and conduit technology that Nextek was developing at the time. So that was my project, which worked out pretty well, because the first job that I got right out of school was at Nextek Power Systems, which was the company, again, that had sponsored my capstone project. And just to give you a sense of the power of the undergraduate degree in engineering that you guys are really about to earn, just a few weeks before, I had been taking classes just like you guys. I graduated, got the job at Nextek, and I was one of 2 engineers in the West Coast office in Sacramento, California. The rest of the company was located out on Long Island in New York. And so they decided to make me responsible for all West Coast engineering operations of the country. West Coast operations of the country. So every engineering decision that Nextek made that involved a customer west of the Mississippi River was ultimately my responsibility. So it's a huge amount of responsibility that I got right out of school. It was a really neat experience. So a couple things that we managed to do at Nextek. First thing was we finished the installation at UC Irvine that I'd started for my capstone project. So here's the visitor gallery now with those solar-assisted Nextek powered lights totally installed. And then moved on to external commercial customers. And the thing that I'm really proud about at my time at Nextek is participating in the first sale of a commercial direct-coupled solar photovoltaic array. That sale was to Whole Foods Market in Berkeley, California. That system is still there, but at the time, it was the very first solar-assisted direct-coupled lighting system that Nextek had sold to anybody. So the company's very first sale was something I got to participate in. So that was really cool, really neat experience to be the first person to be able to do that. In parallel to my work at Nextek, I was also applying to graduate schools. Ended up getting an offer letter at the Massachusetts Institute of Technology, and so decided to leave Nextek and pursue my master's degree in mechanical engineering at MIT. Eventually, I graduated with my master's degree and moved into the PhD program at MIT, and there my work was sponsored by the US Army through the Institute for Soldier Nanotechnologies. The work that I was doing was looking at transport of water vapor through micro and nano-engineered non-woven porous barriers. So the Army at the time was fighting 2 wars in the Middle East, and soldiers were using Kevlar body armor. It was very hot in the Middle East, and the soldiers were not able to sweat through the body armor, and so they couldn't cool themselves, and they would end up getting heat stroke, heat exhaustion, and other heat-related injuries. And so what we were looking at is to try to replace the non-porous Kevlar body armor with something that could stop bullets, but that was also porous. And so here's just some experimental data to show you the type of work that I was doing. So we used latex as a stand-in for Kevlar. It's a non-porous polymer material. And here's a simulation of the temperature of human skin if exposed to long duration sunlight and ambient temperature in the Middle East. through a non-porous barrier. And we evaluated a number of micro and nano-porous barriers that were at the time being made by the DuPont company, and found that they offer a substantial decrease in the skin surface temperature, somewhere between 13 and 14 degrees Celsius. And so what I was able to demonstrate for my PhD is that the Army could actually develop body armor, anti-ballistic, wearables for soldiers that would allow them to sweat through and cool themselves, so they could be more effective in that environment of the Middle East. So I feel like I made a nice contribution to a lot of the great human protection work that our U.S. Army does. So I graduated with my PhD from MIT, and my first faculty job was as a brand new assistant professor at the University of North Texas, UNT, in Denton, which is north of Dallas, Texas. At the time, the College of Engineering at UNT had just been started, so I was a founding faculty member in the Department of Mechanical and Energy Engineering. And we did a lot of energy-related research there, but the work that I'm most proud of is the work that I did on concentrated solar power. So here's a couple of experiments that I developed looking at concentrated sunlight and its effect on surface coatings and its effect on the degradation of conventional photovoltaic arrays. Was able to leverage that research into a relationship with a company called Solar Logic. So Solar Logic was a North Texas-based startup that was interested in using concentrated sunlight to run an organic Rankine cycle for residential and commercial power generation. So here's me and the president of Solar Logic standing in front of one of the solar simulators that we developed so that they could benchmark some of their technology. So after 4 years at the University of North Texas, I decided to trade up to the Milwaukee School of Engineering in Milwaukee, Wisconsin. MSOE is one of the top 10 undergraduate serving engineering universities in the country. So it was a really prestigious place for me to go, a really nice step up. And there I was able to continue my research with Solar Logic. And in this instance, we were looking at their heat collection elements. So these are the elements that essentially operate to collect the sunlight. Sunlight goes through glass tubes and strikes an anti-reflective coating that's coating around a metal inner tube that carries the working fluid that ultimately gets heated up and run to a Tesla turbine, which is the prime mover for the Solar Logic organic Rankine cycle. The issue, though, is that these heat collection elements were not performing the way that they should. And the thought was there needs to be a vacuum maintained between the inner tube and the glass to prevent heat transfer from the hot inner surface back out to the outer surface here. And we thought that the vacuum might be fouling for these heat collection elements. And so as part of a capstone senior design project, we developed this really neat experimental technique where we would heat up those heat elements with boiling water and then watch their cool down and compare that cool down to the ideal that you would find if the vacuum were perfect. So here we've got a technician pouring boiling water into one of those heat collection elements, and you can see the cool down curve as a function of time. And we were able to actually show that that vacuum was not being maintained properly, and it caused Solar Logic to actually recreate their entire manufacturing process to be able to maintain that vacuum better to increase the performance of those heat collection elements. So that was a neat thing to work on. I eventually got recruited away from MSOE to Philadelphia University in Philadelphia, Pennsylvania. Got promoted to associate professor and director of engineering programs. So I was in charge of the engineering programs at Philadelphia University for 2 years. Sadly, just as things were going really well for me and my career was starting to take off, disaster struck. I ended up becoming afflicted with a chronic autoimmune disease called ulcerative colitis, which is an inflammatory bowel disease. Effectively, what has happened is that my body thinks that my colon is a foreign object. And so if left unchecked, my immune system will actually start attacking my colon. And it's a very, very debilitating, very painful disease. And it was so bad and was not properly diagnosed for the first 4 years that I had it, that I actually had to step away from academia. I had to step away for 4 years and was on long-term disability while my doctors were trying to figure out this illness and get me back up on my feet. So during that time, I was effectively homebound because IBD messes with your digestive system and your ability to kind of move food properly through your digestive system. So my family and I moved from Philadelphia to Nashville, Tennessee. I was effectively homebound because of the illness, but I started a company called Engineer Inc. that focuses on engineering education offered through online websites. And so we had a nice partnership with Tennessee State University there in Nashville, where we were looking at a fluid mechanics technology. Effectively, it's an apparatus that's small enough that can be fit into a box and shipped to a student taking a fluid mechanics class remotely online. And so these are Tennessee State University students who are testing the prototype in the laboratory, but this eventually became a product that Engineer Inc. sold to universities who are interested in putting their mechanical engineering fluid mechanics courses online and giving the students a laboratory experience, even though they were taking an online fluids class. So that was pretty cool. Engineer Inc. actually still exists and is located in Gainesville. And from time to time, I check in with them, just to check in to see how things are going. We did move from Nashville, Tennessee to Gainesville, Florida. That was to allow my wife, who is a University of Florida grad, to take a job here in Gainesville. I was still very sick at the time that we made this move, but happily I was able to get connected with doctors at the Mayo Clinic and here at University of Florida Shands Medical. They were able to get the illness under control, and I was able to be well enough to accept a position here in the Mechanical and Aerospace Engineering Department at UF as a senior lecturer teaching the capstone design sequence. So that's effectively how I got here. In parallel to teaching capstone design and being really focused on good teaching, good instruction, and supporting students, I also run a small research program looking at Tesla turbines. So this is the same technology that Solar Logic was using. That's the company with the solar assisted organic Rankine cycle that I've talked about before. Same prime mover. And my interest here is to miniaturize Tesla turbines and look at their performance when they get made really, really small. And it turns out as you miniaturize these turbines, their performance becomes actually quite a bit better than aero-derived turbines at that same small micro scale. So there's a lot of really neat potential. This is a totally open area of research. I'm one of only few people in the world doing it. So if you guys are interested in getting involved in undergrad research, this is a project that's available to you if you guys are interested in working with me. Anyway, that summarizes how I got to where I am now. So I'm going to move on and talk about my goals for the course. So this course really has 4 goals, and these are a bit unconventional, but I want to be honest with you guys. This is really what I want you to get out of Capstone with me. First, I want you guys to embrace and be able to solve with competence open-ended engineering problems. You guys, up until now, have really been trained that there's only one correct answer to any hard technical problem. You solve the problem, you flip to the back of the book, find that you've got the right answer, that's the end, and you move on to the next problem. Engineering design, capstone design is going to be a little bit different. It turns out that there are multiple right answers to problems that you face in capstone, and I want you guys to become really familiar and really comfortable with that alternative way of solving problems. I also really want to prepare you guys for professional practice or grad school if you're interested in going that route. It turns out that a lot of my students, as I've taught capstone over the years at several different universities, end up going on job interviews and talking an awful lot about capstone design in those job interviews. So I want to make sure that you guys have the professional preparation to be really good in those interviews and to convince potential employers that you guys are ready to be practicing engineers. This attaches to goal number 3. I want to make you guys more attractive to employers. We're going to do a really interesting project this semester, which I will disclose later in the semester. Really neat, hands-on, applied project that will make you super attractive potential employers. And finally, I want to equip you guys with war stories. I want to be able to send you off to those interviews to be able to tell potential employers about all the neat stuff that you've done at UF and in Capstone. All right, that's the end.